Welcome to the course Digital Transformation and Technological Innovation. So in the last few sessions we completed our introductory module, that was fundamentals of information systems. Now we move to our next module, that is digital infrastructure. So let's start. Now one important question when it comes to digital infrastructure is that the computer hardware and the software components. So for an organization's information systems, what kind of computer hardware and software components we should be selecting or we should be purchasing or acquiring, so that our organizational processes and other activities are well supported. So that's the starting point. As you can see here, that how should computer hardware and software components be selected to support the organizational information systems. So obviously here the focus is on information systems, the kind of information systems that an organization is having, and therefore what is the best kind of computer hardware and the software that is more suitable for that, that is more likely to support that kind of information systems. That is this whole process is about. So as you can see, the idea is that efficient processing and timely output, because why we are having information system in the first place, data driven decision making, better information sharing, and so many other benefits that we talked about in the previous sessions, right. So eventually we want to improve the organization's productivity, efficiency. So in that regard, whatever data or information that is coming in, that we should be able to efficiently process and in a timely manner. So the output that we are expecting, that we would be generating through our information systems, that we should be able to do in a timely manner, because certain decisions are to be made and certain actions are to be taken in an organizational context. So this has to be there. Now moving on, how do we choose the right computer hardware? So let's first focus on the hardware component here. So how do we make these choices? What is the most suitable computer hardware? So computer hardware that will fit to our business context, our organizational business context, that we need to look at. So understanding its link, that is the computer hardware's link to the computing needs of information systems. So as we said that what kind of computer hardware would be needed, so that the computing needs or the requirement of a particular information system, of a specific information systems, could be met. Then along with that, current and future business needs. Why current and future business needs? Because these computer hardware, these are heavy capital investments. So therefore once you make your investment into servers, other storage systems, and so many other hardware components, then you would like to work, use them or exploit them for your business processes, activities, and other things for a number of years. That means when you are making investments, the future business needs also need to be looked at, because you would be stuck with that computer hardware for a number of years, because they are so expensive you cannot quickly change them, right, and they have their own life, right. So you would like to have your good return of value when it comes to the kind of computer hardware that you have invested in, right. So the current and future business needs. Now how do we figure out current and future business needs? So obviously we need to look at the information systems, its processing requirements day in day out, what kind of production environment it would be running in, whether it would be 24/7 or activity anytime, but not like constant activity. Sometimes there would be certain processing that would be needed, certain interaction through the information systems would be needed, other times it might be idle, right. So what kind of production time that we are talking about, that also need to look at, the kind of uses that goes with it, number of users that will be interacting with the information systems. So many other things, how many modules. So there are so many things within the information systems that one has to look at, and therefore accordingly the computer hardware and the covering the current and future. So in case in future you see that your business will scale, your business will grow, then whether the kind of computer hardware that you are investing in now, whether it will support that growth, whether it will support that additional computational load that might come because of the increase in the number of customers or number of users or number of other such stakeholders and other processing needs. So, let us moving on. So, processing data information, so that becomes a key system aspect. So, whatever we discussed, so it is clearly understood that processing data and information is a key system aspect here, and that is fulfilled by how. So, it is fulfilled by because of the interplay that happens between one or more central processing units and primary storage, right. So, whatever data and information that is being processed. So, CPU is the component that would actually be responsible for working with data, whatever set of instructions that are encoded in the form of the software, the logic that is there in the software that is to be executed by the hardware. Within the hardware, it is the CPU that would be executing those instructions, right, and the primary storage, which is actually the memory, as we will be talking about, would be playing the role. So, interplay between the CPUs and the primary storage, right, the memory. So, these two components will essentially decide how this data information, how fast or slow and which way this data information would be processed. So, these two CPU and primary storage / memory become the key system aspects. Now, let us talk about the central processing unit. So, this consists of three primary elements, right. So, one is arithmetic and logic unit. So, all the arithmetic calculations or computations or the logic computations that need to be performed is done by this particular arithmetic and logic unit. Then the second primary element is the control unit, which controls sort of the data flow and other things. We will look at this in detail. Then there is a storage registers, so which keeps tracks of the instructions and other things. We will look at this. So, these are the three primary elements: arithmetic and logic unit, control unit and storage registers. So, let us look at these three elements one by one. So, let us start with the arithmetic and logic unit. So, we refer this as ALU, arithmetic and logic unit. So, what it does, as I said, performs mathematical calculations and makes logical comparisons. So, if in your software logic there are instructions which are doing mathematical calculations, logical comparisons, then those would be handled by ALU, arithmetic and logic unit within the CPU, right. Then the next one, control unit. So, what it does, it sequentially access program instructions, right. So, there would be lots of codes of lines within the software, so many statements that would be there. So, those program instructions sequentially one by one after another, they would be accessed by the control unit and decoded them, decoded by the control unit. So, it decodes them, accesses program instruction, decodes them, and then coordinates data flow in and out of the ALU, right. So, instructional data that is there, that also needs to be coordinated. So, in and out of ALU, which will actually ALU will actually do the execution. So, control unit will control the sequence and the instructions and the decoding of it and how it will go in and out of ALU for execution. And then the primary storage also, sometimes you will have to store the values, primary storage will come in, right. So, control unit coordinates data flow in and out of ALU, primary storage and even secondary storage, because sometimes the kind of processing that is needed, secondary storage might also have to be used. And then output devices also, output has to be thrown in, displayed somewhere. So, the output devices will also come in, right. Secondary storage, when lots of data is to be worked with, so that will in batches maybe have to store in storage, bring into the primary storage, that is memory, and then one by one instructions will flow in and out of ALU, right, as the ALU executes them. So, essentially control unit is doing all this coordination, right, sequentially one after another, accessing program instructions, decoding them and coordinating data flow involving all these components: ALU, primary storage, secondary storage and output devices. So, that is about control unit. Let us move on. Then registers. So, what is the role of registers here? So, these are high speed storage area, right, because CPU is quite fast. So, it might need some fast support, all kinds, whether memory or these registers. So, high speed storage areas to temporarily hold small units of program instructions and data immediately before, during and after execution by the CPU. So, registers keep this high speed storage. So, these are the areas where small units of program instructions, so not all of it is going to be executed in one go by the CPU. So, we take the small units of program instructions, they are kept at they are kept in temporary storage at the registers, right. So, these high speed storage areas. So, before, during and after execution by the CPU, right. So, this also plays an important role in terms of managing the program instruction different units of it, right. Then we also talked about, when we talked about the control unit, we also touched that its connection with the primary storage, because data flow in and out will also happen through primary storage. So, what is the role of primary storage here? So, holds program instructions and data in close interplay with the CPU, right. So, because CPU is executing a program, so instructions are flowing in, flowing out, controlled by the control unit. Primary storage is holding lots of instructions and data, which will eventually come to the register and then move out of the register and go back to the memory and maybe secondary storage. So, primary storage plays an important role, holds program instructions and data in close interplay with the CPU. This is also called main memory or memory. So, more often than not we refer this as memory, sometimes main memory, and other times primary storage. So, these are the three terms interchangeably being used in a computer context. So, holds program instruction data in close interplay with the CPU, while CPU works through, executes through those set of instructions. So, let us move on. Now, let us consider the CPU and memory. So, these two are important elements, as we understood right earlier also, that CPU and memory are the mainly responsible for us to give a good performance in terms of executing instructions or working with data. So, CPU and memory, they are housed and connected together in a physically closure space called the motherboard. So, within the computer there is motherboard. So, in that CPU and memory are housed and in close proximity, physically closed space, right, and together make up the system unit. So, the word system unit essentially means the CPU and memory, because CPU executes and the memory helps data flow in, flow out in that process. So, CPU and memory are referred to as the system unit, right. Other computer components, what happens to them, how they are in this whole processing. So, other computer components, they are linked to the system unit via direct or indirect connections. So, other components, they also play their role when the results are to be displayed, so that output device will also come into the picture, right, or there is some results that are to be saved in the secondary storage, the secondary storage will also come into the picture. So, these other computer components are linked to the system unit via direct or indirect connection, right. So, when faster connection is needed, then for a particular component, then the direct connection would be preferred, and sometimes slower connection is okay, then the indirect connections might be there, right. So, CPU and memory, forming the main system unit, and the other components having direct or indirect connections to the system unit. Moving on. Now, what is bus? Why we are talking about the bus, its role. So, this is a set of physical connections. So, we talked about the connections earlier, that physical components are linked to system through direct or indirect connections. Now, who is providing this connection? What is the mechanism? So, which component? So, the connections, which particular component is supporting the connection part. So, the bus plays that role. Bus is a set of physical connections shared by multiple hardware components to communicate with one another, right. So, the connection part, the system unit and the other components, and within system unit also a set of physical connections are there. Bus is a set of physical connections. There are lots of buses within the computer system. So, a set of physical connections shared by multiple hardware components. So, multiple components would be sharing these connections to communicate with one another, right. Then within the buses, first one is internal buses. So, what is the role of internal bus? So as the name says, internal, so this quite walks closely to the system unit. So connect CPU, memory and motherboard components, right. So system unit is sitting or housed on the motherboard. So therefore, CPU, memory and any other components that might be there. So for they require high speed communication. So these CPU, memory and these components, they require high speed communication, because they are, these are the main, components, main elements responsible for the actual processing, right. So the internal buses are supposed to be quite fast in this case. So connect CPU, memory and motherboard components for high speed communication. The next step is external buses. So what is the role of external bus? So it connects external components, that means the component which are slightly external to the system unit. So those components we are talking about. So external buses connect external components to the computer, often via ports. So there would be ports more often than not, which would be used to connect the external components, and the buses would be there to facilitate that connection via ports. So what are these components? Monitors, keyboards, storage. So monitors are the output devices that that are there. So any processing that is happening, the results or output of that processing would be displayed on the monitors, the screens. And then the keyboards, if there is some sort of input that is to be typed in, then the keyboards would be used, right. So they become the input devices. And the storage is also there, so secondary storage, some extra storage might also be there that we might want to plug in, right. And then so sometimes some processed output needs to be stored, right. So storage needs to be connected. So external buses provide these connections to external components, right. Moving on. So how to determine the hardware capabilities, because we earlier talked about the information systems, and accordingly we should be acquiring computer hardware which will fit the need of our information systems, right. So that means in that process we need to have an understanding of the hardware capabilities. Only then we would be able to decide what kind of a hardware would be suitable for our kind of information systems, right. So what are the things that we do? We check processing power, speed and capacity. So these three things: processing power, right, the speed, how fast that processing can be done, and the capacity, right. So so all these three put together, right, are important in terms of evaluating the hardware capabilities, right, and how it can support our existing information systems, right. So now we will talk about different aspects of computer hardware and how it connects to the power or speed or capacity, one of these three, and therefore we will be able to form our ways to evaluate hardware capabilities. So which components are responsible for processing? So CPU and memory, as we have discussed. Now what are the key consideration here? So these CPU and memory itself, because these are these form the system unit, and the main component responsible for processing, as we understood, then they become the two key consideration when choosing hardware for information systems. So essentially when we say processing power, speed and capacity, essentially we are looking at the power or speed or capacity of these two components, CPU and memory, right. So let us look at each of these factors one by one. So how to gauge processing speed, right. So we need to know how the processing speed is measured, expressed, labeled in the market, in the computer hardware and the IT market in general. So processing speed measures include machine cycle time. There are other measures that can also be there, that can be added, but the main one is machine cycle time. So that is used to gauge the processing speed. So when we say machine cycle time, it depends on the CPU clock speed, right. So it when measure is machine cycle time, and it depends on the CPU clock speed, where the CPU clock speed is a series of electronic pulses that are being generated, that are being produced at a predetermined rate by the CPU. So every CPU will have its own clock speed. So there would be an associated predetermined rate for generating these electronic pulses, and that will determine in a way the machine cycle time and therefore the processing speed, right. So again, CPU clock speed, series of electronic pulses produced at a predetermined rate by the CPU, right. So this predetermined rate for a given CPU, and this will decide the CPU clock speed, series of electronic pulses that are being produced, and the machine cycle time depends on this CPU clock speed. So therefore processing speed is decided like this. So measure is what for the CPU clock speed, billions of cycles per second. So this predetermined rate is expressed like this, billions of cycles per second, gigahertz in other words. So gigahertz is the measure for the clock speed, billions of cycles per second. So depending on this clock speed, the machine cycle time depends, the machine cycle time depends on this. So you have to look at when you are looking to invest into a server or computer and you focus on the CPU component, you look at this billions of cycles per second, the CPU clock speed that is there, it would be expressed in the gigahertz. Then when it comes to execution of program instructions, right, each program instruction takes at least the same amount of time as the interval between pulses. So this CPU clock that we talked about, and electronic pulses are being generated at a predetermined rate. Now when it comes to execution of program instructions, so each one of them at least at the minimum it will take same amount of time as the interval between pulses, right. So that will whether it gets executed within that, or but at least that much will be counted, right, at least the same amount of time as the interval between pulses, right. The shorter the interval, the faster the execution, right. So if this interval between pulses is shorter, right, that means in a way the electronic pulses are being produced at a higher rate, then the execution will also be faster. So because the gap between pulses will reduce if these electronic pulses are being produced at a faster rate, the interval between pulses get reduced, and therefore as a consequence that cycle time will reduce. So shorter the interval and the faster the execution, right. So essentially as we said, execution of program instruction, the speed of this execution depends on this. So speed in personal computers therefore is specified in a range of multiple gigahertz, right. So we need to look at this number when we are looking at the speed aspect of personal computers, for that matter any server. We look at this range of multiple gigahertz, that would be used, that is 1 unit, and that is how the speed is specified. Now we come to the memory part of it. So what is the main feature of memory? So main feature of memory is to speedily provide the data instruction to the CPU, because CPU is the clock is working fast depending on the electronic pulses and how fast it is. So in that process it will execute the instructions, right. So the memory has to supply the data instructions to the CPU in a speedily manner, should be able to match the speed of execution for better or a speedy output. So it depends on the data size and the memory capacity to hold it, right. So what kind of data and the size of data that you are working on, and whether there is sufficient memory capacity. So capacity comes in. So for the memory, the capacity part is important, how much data the memory can hold off, and therefore it will be in a position to speedily supply that amount of data and instructions to the CPU, and therefore faster processing could be facilitated. So memory and CPU, what are these at a hardware level? So these are distinct integrated circuits, right. So distinct, so in a way they are similar, that both of memory and CPU in terms of how they are in terms of electronics of memory and CPU, they both are integrated circuits, but obviously distinct different kind of circuits are there, right. So what are integrated circuits? So integrated circuits are produced by applying the same manufacturing process. So the manufacturing process to produce these integrated circuits is same, that is whether it's about CPU or memory or maybe any other hardware component. So produced by applying the same manufacturing process onto silicon wafer. So what is a silicon wafer? Silicon is a semiconductor material, and silicon wafer is a thin circular slice of semiconductor material. So, thin circular slice of semiconductor material is taken, that is referred to as silicon wafer, and the same manufacturing process is applied onto it to produce the integrated circuits, right. And when this process is applied on silicon wafer, then what we arrive at, what we produce, we create rectangular chips, ICs, right. So, chips or ICs are rectangular actually, and a circular slice of semiconductor material is taken, which is silicon wafer, manufacturing process applied to it, we produce ICs of different kind, memory and CPU, and similarly for others. So, ICs, they contain vast number of transistors, resistors or capacitors. So, different combinations of transistors, resistors or capacitor, which are typical electronic products, electronic components, electronic devices in a way. So, transistors, resistors, capacitor, typical electronic devices. So, the ICs are combinations of use vast numbers of different combinations of these. So, that was about CPU and memory and how there are more details, the processing and other components within them, ICs and different aspects that we talked about. Now, let us move on to the data part, right. So, here when we say data is stored in memory as a combination of on-off states. So, when we say ICs, and ICs being a combination of having vast amount of transistors, capacitors and resistors, transistors and capacitors, IC being a combination of that. So, essentially when we say data is being stored through let us say talk about memory, which is in IC. So, data is being stored. So, how this data is being stored? So, in an on-off state form via transistors acting as microscopic switches. So, here transistor play main role because they are working like a microscopic switches, and they in a way facilitate these two on-off states, right, where each on-off state is referred to as a bit, right. So, on and off, these are the two states that are maintained through the registers, right. And so, when we say data is stored in memory, so essentially these two states are being managed through transistors, right. So, each on-off state is referred to as a bit. So, therefore, it corresponds to two numbers, on 1 and off 0, right. So, these two numbers can be managed through this on-off state mechanism via transistors. It could be either on or off. So, therefore, it could be either 1 or 0, right. Now, this is bit, right. So, bit is each on-off state and which is 1 or 0. Then we come to byte. So, what is a byte? This is 8 bits form a byte. So, represent a single character of data, for example, A. So, a single character A can be represented using byte, which needs 8 bits. That means 8 on-off states would be taken to represent, would be needed to represent a single character, for example, A, right. So, 8 bits form a byte. Then we come to 1 GIB. So, 1 GIB is GB byte. So, what is this? So, 1 GIB storage capacity means 2 to the power 30 bytes, right. So, byte is 8 bit and 2 to the power 30 bytes are needed to represent 1 GIB, 1 GB bit, 1 GB byte, right, of storage capacity. Here this is more like a base 2 definition, binary definition, right. When we say GB byte is base 2 binary definition, and we express that in the form of 2 to the power 30, 2 being the base, right. But there is another commercial labeling that is done to represent this storage capacity. So, there this is commercial labeling that we typically see in hard drives. This one GB byte having storage capacity using binary definition, that is more seen with the memory, and the other one is more common commercially with the hard drive. So, what is this other one? Follows a different standard, and here we often see that 1 GB gigabyte. The earlier one was GB byte and this is gigabyte. Storage capacity means 10 to the power 9 bytes. So, this is a decimal definition base 10. So, this is a decimal definition base 10, 10 to the power 9 bytes gigabyte storage capacity. This is a different standard that is followed in the case of hard drives, the commercial labeling. Memory, more often than not we use the binary definition, 2 to the power 30 bytes for 1 GIB. Now, example is, let us say digital storage capacity label of 100 GB. So, when we say 100 GB, when you see that printed on a hard drive, so this might actually be shown as 93 GB or GIB within the operating system like Windows and others. So, because the actual storage in the form of GIB is different, because that is decimal notation. So, different value comes in, but the labeling is of 100 GB, which is for more for commercial region, right. But you see 93 and 100 are very close by. So, there is a approximation that is happening here, right. So, the actual one is 93 GB or slash GIB actually, and the commercial labeling for the hard drives is let us say 100 GB. So, but values closely corresponds to close or rough correspondence between these two. For example, 2 to the power 10 is 1024, right, which is approximately 1000, that is 10 to the power 3. So, 10 to the power 3 in decimal definition 1000 is roughly corresponding to 1024, that is 2 to the power 10. So, whether it is GIB or GB, there is a rough correspondence that we can have, but commercially in the case of hard drives we use the decimal definition, which is we say 100 GB or something, or 1 GB something. In case of memory also we might say 1 GB, but it is actually 1 GIB, and it is a binary definition. So, at this point let us stop. We will continue our discussion on this module digital infrastructure next time. Thank you.